So I would like to introduce Ann Bowen. Ann Bowen is one of our researchers here at TAC with our visualization group. She is also highly involved with our education, and she manages our Visualization Institute that we do every summer. And she's going to give you guys a walkthrough of the various visualization resources that we have here at TAC and in HPC in general. So with that, I'd like to introduce Ann. So, all yours.
All right. Hello, everyone. Let me get my slide share.
Ann.
Okay, before I get myself. All right. Thanks for the introduction, Charlie. I am Ann Bowen, and I'm a member of the Scalable Visualization Technologies Group here at TAC. Today, I'm going to give you a survey of the scientific visualization resources at TAC. So it is meant to be more of a practical guide, so I'll kind of focus on more of the applied aspects of visualization. It's kind of the inverse. Usually when we give the longer talk, we give an introduction to scientific visualization in general, and then kind of a guide using our machines, and then we go over remote viz. But today I'm going to kind of do a backwards presentation and give a quick overview and then a quick start for remote visualization, and then talk a little bit about visualization strategies and best practices for working with larger data. So this is our group at a glance. We maintain and create the HPC software and tools that are run on our systems, and then also research novel ways of interacting with data and providing direct support for scientists who use our systems. So the projects range from optimizing rendering on large systems. So we have, I'll talk a little bit more about this later, but we have a collaboration with Intel and some other partners called SDViz, Software Defined Viz. Data analysis tools for doctors. We have a collaboration with Dell Medical School where we work on different ways to look at CDC and other healthcare related data. We have a collaboration with a group at University of Minnesota looking at VR applications for neuroscience. And then also a number of projects that look at optimizing high resolution tile displays and user environment. So I'll have some examples of that later. And we have some of the visualizations we've created in collaboration with scientists in that link there for the SciVis gallery. And I also have some examples at the end of the slide deck. I don't have time to go through them, but you can browse them. So here's tax systems at a glance. So this, the content from this page is extracted from this link here at the top, but I mainly want to just show all the systems and kind of which ones we support viz on. Remote viz, and by remote viz, I mean the ability to be able to log into a machine and interactively have a graphical user interface or a visualization application like Paraview. On a lot of machines, you could do something like run a job that might output images or some kind of visualization of that sort. But by remote viz, we mean the ability to interact with the system as if you were sitting there with a remote desktop. And the ones in orange, so Frontera, Lone Star 5, and Stampede 2, we support our full visualization stack, meaning we would have Visit, Paraview, VTK libraries, VMD, things of that nature. But we'll go more into those in a moment. So our old remote visualization model used to be that you would run your simulation on the HPC system, and then maybe you'd have your data archive, and then you would transfer that data to our visualization resource. And then from there, you would connect to the remote visualization resource from your local laptop and run your viz there. Now that has changed as data set size increases. It's impractical to move data from the simulation machine to a visualization machine. So as you can see here, even in the best case, you know, the time goes beyond what it takes to have a cup of coffee and come back and have that file be done transferring. So the new model is to have every node be a visualization node, so you can perform your visualization in place. So this is just a quick history of what this has looked like at TAC. So it used to be 10 years ago, when you had Ranger or the original Lone Star, you would run your simulation on those machines, and then we would advise people to move their data to Spur or Longhorn or visualization machine for their visualization. A little bit later on, we had Maverick, which was a visualization dedicated machine, but also ran a lot of other GPU intensive jobs. And then Stampede, we used to have the VizQ, so you would maybe run your jobs on the compute nodes, and then we had some visualization nodes. So now the way things are looking with Stampede 2 and Frontera is that every node is a viz node in a sense, and you can access all the visualization applications you would need from every node and wouldn't have to move your data anywhere. So this is just a graphic to show the new visualization model. We have our HPC system and your data archive, and then you're connecting directly and running your visualization that way. So VNC stands for Virtual Network Computing, and it's the graphical desktop sharing system that we use to remotely connect to another computer. The reason we use it is that it's very efficient. It relays the mouse and pixels back and forth, so it's a pretty seamless user experience. Now we also support DCV, which I'll talk about when we get to the Quickstart tutorial. And one thing I wanted to point out is that we suggest that you use VNC and not just use X forwarding or SSH-Y for any kind of graphics. If you just need to check something, like if you did write out an image and you want to look at it and make sure that it's okay or something like that, you could go ahead and use port forwarding to look at that image. But if you want to run something that has any kind of graphical user interface, we suggest that you use VNC or DCV for that purpose. So here's the, I just wanted to mention the DCV, the desktop cloud visualization. It is a commercial product, so we only have a limited number of connections. We do have job scripts that will try DCV, and then if that fails, it'll automatically connect to VNC. That way you don't have to deal with the frustration. If you just want to get an interactive session going, you don't have to just keep trying DCV until it works. You can try DCV, and if all of the licenses are used, then it'll defer to VNC. So this has made possible the ability to compute on every node rather than relying on having a visualization machine or visualization nodes that require the GPUs through the software-defined visualization software stack. So this is a collaboration with Intel, Kitware, and a couple of other universities to support visualization on workstations without the memory limitations and cost of GPU-based solutions. So existing applications can be enhanced through the high-performing parallel software rendering libraries like OpenSWR, Embry, and Osprey. So we'll see OpenSWR again more in detail, because that's what we use now for all the OpenGL applications. I think for people that have used TAC in the past and VNC, you used to VGL run and then your application name. Now we use SWR and then your application name. Many major visualization tools such as Paraview and Visit and VMD adopt these SDViz libraries like Osprey and OpenSWR. And then you can also use these separately for your own. If you're developing your own visualization application, you can use these directly. And there's more information, a lot more information on this link right here, sdviz.org. So this is recapping kind of what we saw from my introductory graphic. Frontera, which is will be available soon, Stampede 2 and Lone Star 5 support both interactive and batch visualization on any compute node, and also use the software-defined visualization stack. Wrangler and Maverick 2 allow for remote desktop connections, but we don't have the full visualization software stack. So there's a lot of other applications that people use that have a GUI, or they want to have that desktop environment to a remote machine. So that's why we have that for Wrangler and Maverick. But just because of the system architectures and various reasons, we don't support the full software stack. So as I mentioned, we use the Intel OpenSWR library to render raster graphics with OpenGL and the Intel Osprey framework for ray traced images within the software stack in the visualization software. So SWR would replace VGL run. So the tests were GLX gears. Now would replace VGL run GLX gears. And OpenSWR could be loaded by executing the model, by executing module load SWR. So just really quickly, I wanted to give an overview of another important part of research of our visualization group, which is harder to talk about in detail for this kind of talk. Usually if we have an in-person talk, we have half of it where we go into the Viz Lab and play with more of the immersive and interactive visualization technologies. But here I just have a couple of slides to recap what we have. So we have a Viz Lab on the main campus where we, it's open to all UT faculty, and it hosts a very large tile display, a multi-touch display, a couple VR headsets, and some experimental technologies like using motion, the Leap Motion, Google Glass, and touch table, and a Z-Space, which we'll see a picture of in a moment. So just different ways researchers can come in and we can help them try to use these technologies to enhance their research. And then also here in this building, so the main campus here at TAC has kind of two parts. One is on the main campus, and we have a north campus where the actual Texas Advanced Computing Center, the bulk of, is hosted. And here we kind of have more of a experimental human data interaction lab where we do a lot of research into configurable display. So you see this image here where there's some screens. They're just standard large monitor screens, but they're they're reconfigurable so that you can kind of change the display based on the data and what you would want to see. And I have more information about that in a couple of slides. And then there's some example projects at the very end if you're more interested in that project. But the idea is how to make a room kind of more like a holodeck, where the environment could change based on the kind of data that you want to visualize, and based on the needs of the scientist, you could change the room. So change the screens, use gesture detection and things like that to navigate with the data. So now I quickly want to go over the Quickstart tutorial for how to launch a VNC job. So as I mentioned, it's launching a VNC job, whether it be through SSH or the Viz portal, will give you pretty much the same result. Same with the DCV. So if you use DCV, VNC via the command line or the portal, you'll end up with something that looks like a remote desktop with a window manager, that can allow you to interact with the remote machine as if you were sitting there. In the full tutorial, I'm going to kind of just go over the basics to kind of get you started in the easiest possible way. The full tutorial is, if you follow this link, you can get the full tutorial. And then also my slides contain, I'm going to kind of breeze through a lot of them, but if you want to follow the SSH portion step by step, you can review those in your own time. But I feel like the link here has a very good, you can follow through that step by step and should be able to get on with no problem. So just an overview really quickly of what we're doing. We have our local system and then our remote system. We want to connect to the remote system, whether it be by SSHing or so SSHing to Stampede2, say, or via the Viz portal. The Viz portal takes care of that for you. You log into the Viz portal and then you can request a job from there. But for us, we're going to, if you're from an SSH terminal, then you're going to submit a slurm job for the job.vnc to start a VNC session. And that's going to start the VNC server on the remote node. And it's going to run, just run like a regular job. And then after that, you're going to start a VNC client on your local system. And then you're going to connect them, and then that is going to allow you to run any program on your remote system. It's going to appear like it's on your desktop. So as I said, there's two primary ways of accessing VNC, the portal, which is a simplified web interface for viewing your allocations, submitting jobs, and interacting with remote biz sessions, and then via SSH as well. So I recommend using a VNC viewer. When we look at the portal, we can see that it's very easy. There's a separate tab that opens that has that desktop view. But if you plan on doing anything more than just checking up on something quickly, it's much nicer if you have the VNC viewer installed locally. So when I'm at my desk, I have two monitors, and I have one monitor that has my big monitor with a large desktop view open to Stampede 2, and then Paraview running, and it really seems like I am just sitting right there at Stampede 2. If I have a Mac, and I find that the default screen sharing works well, but also real VNC. I like, a lot of my colleagues like to use tight VNC. So here is a look at the Viz portal. We try to make it easy by simplifying a lot of things in the interface, but it lets you do all of the basic things you need to do. And you can interact with VNC without the hassle of manually managing your jobs. So I'm not going to, in the longer tutorials, we usually go through how to, we all do this together. So today I'm just gonna show you, but if you run into any problems, if you try this later, feel free to reach out to me directly, or we have a ticket system. Yeah.
Could you stand up so the camera can focus on you over there?
Oh yeah,
Sorry.
Yeah, it's actually not a lot. I'm pretty short, so like the difference between me sitting or standing isn't a lot, but is that better?
Okay.
I mean, this is the best I have because I can't get any taller, but it's actually, we have stand-up desks here, and then for me, it makes no difference if I'm sitting or standing because I'm that short. Okay, so notice here, if you go to viz.tac.utexas.edu, you can see, so this is a bit of an older interface, and we're working on a newer one that also has Frontera, but you can see you have the resources that you can submit to. There's a drop-down menu where you can select your project and your session type. So there's VNC, Jupyter Notebook, RStudio. Now we no longer have the separate TensorFlow and Jupyter Notebook, but basically gets to select whatever type of session you would like. The queue, we recommend using the development queue on Frontera and Stampede 2, just because that will allow you to get on a little bit faster. The time limit is shorter, but if you just need a session and want to get on quickly, the development queue is the way to go. So then the first time you're going to need to set your VNC password, and it'll prompt you to do that. And then you hit start job, and you just wait for your job to run. On the development queue, it's pretty quick. It should only take a few minutes. But you'll see an interface like this where your job has been submitted to the resource Stampede 2. And then it'll say your job status is queued for a moment, and then once it's running, usually it says running for a few seconds, and then the interface kind of changes to look like this. Often it'll by default switch over to your desktop view in the browser, so you can enter your password here, and then you'll see the desktop view open up with the window manager. Or in a minute, I'll show you how you can copy and paste that job information and open it up in a standalone VNC browser. But it'll look something like this. So you'll see, and you can select, this is more advanced for this class, but you can change the window manager and things like that in your, by changing your .vnc startup. So you're not restrained to using only one VNC or one window manager. And this is just a preview of kind of what it looks like now under construction. So we have Stampede 2 Frontera and Wrangler, and then we'll also support VNC, DCV, the Jupyter Notebook, and RStudio kind of from this one interface, and everything else looks pretty much the same. We're just adding the support for those other for Frontera, and then also DCV directly from the Viz portal. And the job script that is run here will be the DCV to VNC. So if you don't get a DCV session, because all the licenses are used, it will default to opening up the VNC session. And it'll look the same. So here, when you see the jobs, you have the option, you just click the button to open DCV in browser. And this is the same, it looks the same whether you're running a DCV job, a VNC job, or a Jupyter Notebook job. It'll have something about open the job that's running in a browser. And then it also tells you where your session is available at. And I'll show you how to get that running in a separate VNC viewer for VNC in a moment. For DCV, it has its own, it'll redirect you to a different web page where you will log in with your TAC login and portal that you use for SSH there. So this is separate, different from VNC. And VNC, you have a separate VNC password that's unique to the VNC session. But for DCV, you just use your same TAC login that you use for SSH. But the end result is the same. You'll end up with a terminal with the window manager that looks the same regardless of how you started it. One thing to note for people that do not go the SSH route, it is useful to learn to know how to SSH and to know a few things about what's going on in the back end. When you launch your VNC or DCV job in your home directory, it's going to make a VNC server or a DCC server.out file. And sometimes if a web portal is having issues, if you log into your home directory and look at this file, you can actually see the information, so it says your job is running and it tells you how to connect. So you could always use this information and connect directly to your session without having to go through the portal. So you use your portal to launch the job, but if something happens with the portal where it seems to be locked up or it's not giving you the information, this is just another way to access that information. And I recommend for our classes, sometimes in the past, when we've had a visualization tutorial for groups that aren't necessarily eager to use SSH, we found it's better if people at least know how to SSH and to be able to kill jobs and things like that and monitor their jobs, because you can submit jobs via the Viz portal, and it's harder to manage them in a way that where you can just view all the jobs you have running and then use cancel to kill the jobs and things like that. But for anyone that's interested in doing this that isn't familiar with SSH, there is a quick summary in the user guide that kind of tells you how to do all the basic things you would need to do to a job, mainly viewing and killing them. So even if you're not extremely tech savvy, knowing a little bit how to log into the machines and check the status of your jobs is really useful. So this is just another example. So if you also want to start your Python notebook, you just select that option and hit run, and then it will ask you if you want to open Jupyter in a browser. And this is just kind of what it'll look like once you start your Jupyter notebook running. And again, we don't have time to go over this in detail today. But I just wanted to point it out. Something that we get a lot of tickets about is that I wanted to remind people that when you open your Jupyter notebook, it's going to use the default Python that's in your environment. So if you want to, by default, use Python 3, you need to edit your environment to load that module. And then you could also add an alias to have Python be Python 3, for example. So I want to show you how to access your VNC session with the standalone viewer. So once your job is running, we've seen this a couple times in the slides, there's this section right here where it gives you a URL for where your session is available at. You can just copy that, just select it and copy it, and then go to your favorite VNC viewer that you've downloaded. As I've mentioned, it works on Mac, just the default screen sharing works well. And this is kind of an old screenshot with Type VNC and Longhorn, but they all work the same. They'll have something that says your VNC host that you want to connect to, and it'll ask for your username and password. And this is your VNC username and password, or the username is always the same, but the password is going to be the VNC password that you set up. And so this is SSH access. I'm not going to go over in detail. I'll just go over the steps really quickly. So you would log into your machine, then you would submit a remote VNC job. So that is located in share.slurm.job.vnc. And then once it's running, you would look at the VNC server.out file, and that looks the same as that little bit that I showed you before where it tells you instructions at the end. Your VNC server is running and it tells you to create a tunnel and then connect to localhost. And really the extra step that people tend not to like is that tunnel, but that is for security reasons. That's something that the web portal sets up for you. And then you can see at the bottom, so this is from your local machine. Another thing that people tend to get confused about is they try to set up a tunnel on the remote machine rather than their local machine. But after you look on the remote machine and you get this information about the port number, then on your local machine, you would set up the tunnel like so. And this is in the user guide, and the link is right up here. If you forget any of the details of these steps, but you would have SSH-F-N-L, your username, who you're connecting to, and then you have the port, the machine, and then the port again. That will set up a tunnel on your local machine, and then from there you can just type, you can just paste this local host and then the port number in your favorite VNC viewer, just as we did before. So this is just a closer look at the job.vnc. Everything that you can edit here, which is just this little section, we don't recommend that you edit anything outside of that. This is just the job parameters. But for example, if you want to have a unique name, or if you want to change, the runtime or the number of nodes, if you want a parallel job, you can set that here. All of these things are also, there's command line options that you can add to your SBatch shared doc slurm.job.vnc. So it's not necessary to edit this if you don't want to. And we recommend, unless you really have a reason where you want to play with these options, it's better just to use the one that is always at shared doc slurm, shared doc slurm job.vnc, because we might make modifications to that to improve it. So if you were always using your local copy, you might miss an update that was made. So we recommend just using that one, but you can make a copy locally and edit that one and just submit your local job.vnc if you wish. So once you're on this portal, it is the same as if you were SSHing and just had a normal terminal window. You can open a terminal window, use module avail, and there's a talk later that's more specifically about TAC resources. So I will defer to either looking at the user guide or waiting for that talk to learn more about the module system. But module avail would tell you all the available applications, and if you want to know more about what is there. So there's a couple versions of ParaView, for example. So if you type module spider ParaView, it would tell you all of the available modules. And if you want to find more information about how to run a particular application, so let's say if I wanted to know more about how I would run ParaView, I could do module spider ParaView /5.6.0, so the specific one that you want, and it'll tell you any dependencies that you might need to run, or maybe if it's linked to a particular MPI or Intel build, it'll tell you that. So for ParaView, and this is a bit older, so I'm not sure if it will be the same for the most current ParaView, but for ParaView 5.6, you need to execute module load, Intel 18, IMPI 18, Qt5, SWR, and Osprey, and then ParaView. And then it'll notify you that it has, if it needs to reload any of the default modules, then it'll alert you of that. And then to actually run ParaView, you would type SWR ParaView, and then it'll open up in your remote desktop view. So this is just a list of some common visualization applications on our machines. So there's ParaView and Visit, which are both general purpose parallel SciVis, BMD, which is a molecular visualization application, OpenCV for image analysis, YT, that's an astrophysics visualization application. VTK is a visualization library. QGS, I mentioned that's not really on our machines. It's available at DesignSafe, but I like to mention it just because not a lot of people know Design Safe is made for natural hazards, earthquake scientists, but there's tools there that you can use for any kind of data. So if you need to use QGIS or any related geographical information packages, you can still use Design Safe with your Exceed TAC login. So it's handy to know that it's there if you want to use any of those kinds of applications. And then also open source, as I mentioned, which is our OpenGL compatible software renderer. And if you need to know more, I like to remind people that there's a software search in the Exceed portal where you can look for something and see where it is, or also if you want to know, is Visit installed on any other machines, things like that, you can search there. And I included some links here just to the ticket system and other ways to get help. The Reserve the Viz Lab is not relevant unless you're actually here, but if you are UT faculty or UT student, faculty, or staff, you can reserve the Viz Lab for whatever you would need it for. Oh, well, one other thing I made peer review and visit in bold because we tend to focus on peer review and visit for our trainings. And the reason that we do is because it's one of the few general purpose, open source, multi-platform parallel data analysis and visualization applications. And it's really good for general purpose rapid visualization. It's built upon the visualization toolkit, and the interface looks the same whether you run it locally or remotely in serial or in parallel. So a lot of times for our trainings that we have here, we have a kind of a smaller data set and have people just download peer review or visit locally, and then we try something out. But if you launch it in the way that I just mentioned, it will look the same. The interface will look the same. So it's nice because it's easy to learn and then easy to scale up as your data needs gets larger. It works best with data that is or can be represented by a grid. A lot of the algorithms a lot of the visualization algorithms work best with a grid, and it has some filters that will try to represent your data by a grid. Let's say if you have like a list of points, but they don't work extremely well. So if you have very large data, you might want to try to find another way to massage your data before you put it into peer review. But another thing I'd like to point out about Visit and peer review, it's not the best for all data types. So for example, if you have molecular data, if you're doing some kind of molecular viz, while Visit and peer review can read in molecular data, and they, it has some filters for representing ball and stick models and things like that, it wouldn't know anything about secondary structure or, protein representations or things like that. So, if you have molecular viz, we would recommend that you use VMD, and also for if you have astrophysics data and you want to visualize that, Visit can do that, but often if you use something like YT that's a specialty software that's designed for that kind of data, often it's a bit more flexible and a little easier to use. A lot of, because Visit and peer review are so flexible, it is possible to do a lot of things, but sometimes it's more hassle than it's worth if you already have the option of specialty software already existing. Sometimes the advantage with Visit or peer review is that it's in parallel and it can work with really big data. So I've had some data sets where maybe it would be easier to use something else that's more specific to that data set, but then because it was very large, it was easier to use peer review and be able to run in parallel and get some kind of view of it. If you have really large data, sometimes you don't get to be as picky about what kind of visualization software you want to use. And also, we tend to focus on support for larger data sets and visualization tasks, and I mean that our group tends to focus on that, and also in our trainings we tend to focus on that, just because the people that need help are the people that just can't download their data to their laptop and use Excel. Right? It's the people that their data is too big to do that, or they have more sophisticated visualization needs. That would be the data can't, because either it would take too much time or just too large, like it won't fit on your laptop's hard drive. So it can't be moved off the system where it is computed, or it's so large, the visualization task requires parallel systems for enough memory and or compute. Something that's interesting about visualization that people don't take in mind is lots of times there is kind of a visualization, a memory bloat. It's going to require more memory if you have 100 gigs of data, and then you want to represent it by some kind of surface, that's going to be extra points to represent the geometry associated with that. And then if you have ISO surfaces or something in addition to that, you might need more memory than your data set. So oftentimes, a lot of visualization tasks require more memory. And most people that have small data that they can visualize on your laptop, we don't really hear from them a lot. They don't come to our trainings and they don't need help. So that our focus tends to be on larger data sets and visualization tasks that need HPC resources. And we tend to focus on scientific visualization tools and tutorials. So I just wanted to clarify what I mean by that, because really all of the research topics we have here are scientific. But when we talk about scientific visualization, we generally mean data for which the spatial representation is given or known. Often gridded data, but oftentimes with geodata or molecular data, it's not really gridded data. And information visualization chooses a spatial representation for what is otherwise abstract. So if you want a network diagram to describe relationships and things like that, that's kind of a different area of Viz, which we still, they tend to overlap a lot, but a lot of what our group does and a lot of the support we provide in our trainings and tutorials tends to be SciVis type data, working with gridded data mostly. So the power of visualization, it allows us to see the science quickly. I don't know, this was the visualization showcase winner from SC16, I think. So some of you may have seen it already, but I have a link. We don't have time to watch the full movie here, but it's a really beautiful example of the power of visualization, and it uses volume rendering with selective opacity maps to see the effects of an asteroid hitting the ocean surface. And when you do watch the video, you can see the water vapor and just the effect of waves, the waves both in the water vapor and below the ground that would be really hard to see otherwise. And the researcher we're working with, he had a quote, "Images and animations like these give us insights into the physical processes and simulations that are otherwise hard to extract from massive amounts of data. They are critical in helping us communicate our results more clearly." So I feel like it's just a nice example that was done. It was done by Greg Abram and Francesca Samsel, which were kind of a joint appointment between here and Lannel. But the power of visualization is that it allows us to see more than we could get from looking at just the data. Our eyes are very powerful. And whether it be a production visualization like this one that's very, very inspiring, or if it's just you're using Paraview to debug something, sometimes with large data sets, if I just want to get some kind of visual look at it I could just use something simple like a color map to look at the data and see if there's any outliers and things like that. So it's powerful to be able to use our eye, whether it be for communicating or for debugging. Okay, so the visualization pipeline, typically going from data to visualization, you have your data source. That could be from a simulation or maybe from sensor data or from an actual experiment, like a physical experiment that you collected data from. And then you're going to represent your data in some way. So maybe it starts out as a table in Excel or a grid. Maybe it's a MATLAB simulation that outputs some kind of a grid or a list of points, or maybe a specialized proprietary format from some kind of engineering simulation. After that, you're going to use a visualization algorithm. So something like, let's say you have a grid of temperature data from some experiment, you could use a cutting plane to kind of see what the interior looks like, ISO surface to connect scalar values that have the same value, or if you have vector data, maybe a streamline or a field of vector glyphs like arrows to kind of get a sense of the flow. And then finally, from the 3D model representation, you want to actually generate pixels from that model. So that's the rendering step. So it could be something very, very quick if you have large data and you just want to get an idea of what the general shape is, or it could be something, you could use more sophisticated ray tracing techniques. So that asteroid example had very, very nice rendering and is very impressive. But if you wanted to do something quickly or interactively, then you might just have something that is not quite as compute intensive. And finally, you render that to a display. It could be just an output image to a file, a screen, maybe it's your destination is a VR headset, multiple screens. And then from there, often we iterate and refine according to our needs and goals. So maybe if our goal was to have an interactive view, let's say you're still in the debugging phase and you want to look at your data and explore and find a good view and see if everything looks correct. Maybe you want a very, just like a wireframe representation. So you don't want to use surface rendering at all, or maybe you just want a point cloud. You just want to have a look that you can interact with quickly. That would be different than if you, say, are creating a video for a visualization contest or for a publication or for a presentation. And often maybe if you have a headset that you're trying to target, or if you want to target Google Glass, you might need to specialize how you're going to render that data so that it fits with your output format. And then also you might want to change your techniques just to add insight. Maybe you find that the cutting plane, it's still, you have a cutting plane, but there's still a lot of data that's obscured. So you want to change the transparency. Maybe you want to add something else. Add another filter, add another visualization algorithm. Or you need to refine your simulation. Maybe the grid, you discover that the grid is too coarse, so you need to have a finer representation. Maybe if you are doing something with interactive viz and it's too slow, maybe you want to change from just whatever, maybe if originally your data was just a table from Excel, which you could technically read into Paraview, but it's not optimal. Maybe you want to have a more optimized representation, or even use a parallel file format to make that rest of the process a little faster. And then even you could find things in your final image that might make you want to change the parameters of the experiment. So if you have a simulation, maybe you could adjust the simulation parameters. And our goal the thing that we're working towards is having it be so that you could perform some kind of computational steering or in situ viz, where this is all happening in real time. And so you're running your simulation maybe, and then you're looking at the results and able to change the parameters based on what you see right away. So that doesn't happen very often for large data sets, but that's kind of the idea. If we could, and the group here, our group here that's working on improving the rendering and making rendering more performant and faster, is kind of going towards that goal of in situ viz and being able to interactively visualize your data, instead of rendering out data and then waiting for hours and looking at it and trying to figure out how it needs to be changed, kind of having this done in an interactive fashion. So let's see, I have about 10 minutes, correct? Charlie, yeah? All right. So I'm gonna have, these are some examples of data types. Oh, the last thing I forgot to say about why we teach Paraview and Visit in our classes is another nice thing is often we want to talk about SciVis concepts. So kind of the input data types, the data representation, and the algorithms and filters. Another nice thing about Paraview and Visit is they support all those. So in our classes, in our longer classes, we kind of do this together. We talk about isosurfaces and then we use Paraview to look at those. So it's kind of a nice starting point for talking about all of the different aspects of visualization, going from input data type, it's going through the whole pipeline. So the input data type, the data representation, and the filters. So here I mentioned Paraview Visit support, but this is also true for your own. It's so general that it kind of applies to the general Viz application. What kind of data can you put into your Viz application? So structured grids, so whether it be uniform rectilinear grid or curvilinear grid, and I have some graphics here just to remind us of what that looks like. Unstructured grids, point data or polygonal data. So like this teapot, or things that you see in computer graphics, a polygonal representation of an object. AMR data, which is when you have various resolutions of grid depending on how detailed you need for your simulation. So a good example is a lot of astrophysics simulations. They might need to have a very rough, large grid surrounding their simulation point to make sure things like the gravity are correct, and then where their actual simulation is, they might need a very fine grid. And there's other specialty formats too. Our peer review tutorial goes more into this, and I have the link at the bottom for the peer review tutorial. And then here's some quick examples. So this is LiDAR point cloud data of a forest. Point cloud data is not ideal for peer review because, as I mentioned, peer review likes gridded data. Oftentimes when you have point data, sometimes it could be represented by a grid. So it's worth putting your point data into a grid format if you're planning on using something like peer review or any of the BTK visualization algorithms. Here's an example of a grid. This is from Hurricane Ike, which was a long time ago now. But regular grid, all of the voxels, all of the cells are the same size and shape. Here's curvilinear from engineering model. And then here is an example of polygonal data from 3D modeling. And also, this is an engineering model that has kind of a composite, a bunch of different kinds in the instructor grid. It's in a regular mesh that has tetrahedra, prisms, pyramids, hexahedra, all kinds of different things. So you can also read that kind of data into peer review. And here is non-mesh connected point data. It's molecular data. So the important thing for if you have larger data is that structured and unstructured grids use much, much more space and compute than regular grids. So oftentimes, if you have unstructured data, it's not really an option to make it into a regular grid. But for some data sets, if it's not performing well and there is any way that you can make the description of your data a little more compact. So there's often, you can specify a grid explicitly where you specify the X, Y, Z and scalars for every point. But if that grid is kind of regular, you can use a grid notation where you just specify the origin and the offset and then all the values. So if you have very large data, you need to start making considerations like that into your data set. And oftentimes, as far as the support tickets that we see, we recommend you can try, if you have your table of data, maybe that you output from MATLAB, which is something just like a unstructured XYZ for each point, and then a list of scalar values, and you want to read that into peer review, you can just try it as it is, and if it seems to work and it's performant, then maybe you're okay. But once it starts not performing well, or if some of the more sophisticated algorithms that you want to try from within peer review aren't working, then we could look at trying to use a more efficient representation of your data, if it's possible. Sometimes it's just not possible given the nature of your data. So this is just a summary of kind of the grid types that I showed you all in one slide: Cartesian, regular, rectilinear, structured, unstructured. So I just want to make a note about parallel visualization. Often visualization tasks need more memory than is provided by one node. I mentioned earlier that there's a certain amount of memory bloat associated with visualization tasks, and parallel visualization is only partly about upping the compute power available, but it's also about getting sufficient memory and I/O bandwidth for your problem. I/O is a huge issue in planning how to write your data for parallel access, and placing it where it can be accessed quickly is critical if you have large data. A lot of the times people don't run into this problem because their data set is small enough, but if their data is large enough, we've had projects in the past, really it goes beyond Viz group expertise, where we have to consult with the parallel I/O specialists in the HPC group to figure out what the best strategy is for writing out your data and then reading it into Paraview in the most efficient way. Another thing about parallel data format, so Paraview and Visit, they do run in parallel, and oftentimes the different visualization filters are parallelized to different extents. And so if you request that you're running Paraview in parallel and you want to run some, like an isosurface algorithm in parallel, you have to keep in mind how your original data format is. If you have completely unstructured data, it's essentially data soup without any additional information. Your application is still going to have to read that process serially, and then Paraview will try to partition and distribute it for the visualization algorithms. Structured data formats are a little bit better because it can decompose it into partitions and read it in parallel, or we'll try to. Paraview and Visit will try to do that. The best case is if you have a parallel format like HDF5, which contain enough information that the sub-processes can import its own subset of data and work on it simultaneously. So it kind of gives Paraview enough information, Paraview or Visit enough information to know how to efficiently handle that in parallel. So a lot of the Paraview native file formats, it has kind of a master file which points to all of the chunks of the data. So that's a good start for parallelizing or for optimizing performance in parallel. So I have 3 minutes. This last little bit is just, so usually after we talk about the parallel data formats, we kind of go into some of the issues of different algorithms and how they're parallelized. That's part of our parallel viz talk. Since we don't quite have time to do that, I just wanted to quickly go over a few of just the basic visualization algorithms. But since we do only have 3 minutes, I think I'm going to skip this little bit ahead, which is just showing an example of 2D terrain and representing that in 3D. And then just talk a little bit about this. This is one of our main examples, a weather example from our Paraview tutorial. So we have a data set which is a function of latitude, longitude, and altitude with a number of different parameters. We have temperature, pressure, wind vectors. And in that tutorial, we kind of build up this visualization. But I think it shows a lot of the it shows a lot of the principles of visualization as well as the power of Paraview to use that. So Paraview has kind of a pipeline view that has your original data set, which you see up here. It says WRF small. And then from there, you can build up a successive animation. Actually, I think it might be fastest. I actually have Paraview open with this. So here's the data file. And when you load in the data file, you can see the extents of the data. And then what we have here is I have one contour where I have the clouds. So I used a particular scalar value to show the clouds. And then I added a slice to show where the land would be. And then I warped that by a height field. There's a variable in the data set called height. So I warped that slice by the height field so you could get a feeling of the elevation. There's a calculator feature in Paraview. So in this particular data file, it had vector data, but it wasn't described as a vector. It was 3 separate columns, which were the VW components of a vector. So in Paraview, you can use the calculator or Python. You can also just use a Python script to create a vector. And then from there, this slice was used just so to make the view less busy, because if you had arrows floating all around the volume, it's a little hard to see. So this slice just extracts one slice of the data, and then we have the arrow glyphs. So but you can see here how we don't want to see the slice. It was just used to slice a particular data plane. And so another nice thing about Paraview, so we have time series data here, which I can step through. But a nice thing about Paraview is if you have time series data, it doesn't load that all in at once. It loads in one time step. It kind of assumes that you might have large data, but then when you hit play, it will repeat the same visualization that you've set up on each subsequent time step. So that is nice. And for this data is really small. It's the one we use for our tutorial on our laptops. So it plays in no time, but if you have larger data, obviously, when you hit play, it might take some time. Often if you have large data, we recommend submitting a batch job where you render out the frames rather than trying to interact with the interface. But since this is small data, I can just step through, I'll hit play, and then we can see, make a better angle. It's going through the example. You can see the clouds and the vector fields moving in time. Okay, let me go back to I think that's pretty much the end. As I said, you guys have the slides, and I have some examples. This is just showing more about our Viz lab that we have here and the VR, and then I have a couple different projects that go on in the Viz group, and then you can also check out the Viz gallery. But I think now it's time for questions.
Hey, thank you very much, Ann. That was actually pretty awesome. In fact, there was one of our commenters online said this was a great presentation.
Oh, thank you. I've never had a comment like that. Usually it's just questions.
So a couple of questions here. First off, from Kayleen Cotter, she wants to know if we have any example visualization data sets that they can try out that are already loaded on Stampede 2. We do have some. She can message me personally. We have some that we designed for benchmarking, so they're kind of larger. But I feel like if you just want to get started, Paraview, if you open up Paraview, it has some default data that kind of comes with it. So that would probably be the best data sets to use, is just the default Paraview data sets. Another question from Alper Kanachi. Say, you may not know this or not, but are there any security concerns using VNC?
Yes, that's why we we ask that you use the tunnel.
Oh, okay.
Yeah.
So SSH tunnel and then launch your VNC.
Yeah, and it won't let you. It used to be that we recommended that you use the tunnel, but if you didn't, it would still let you. But now, if you don't use the tunnel, our sysadmin here will email you personally. Tommy, I did this once because I just forgot and I was debugging something, and it will email you and say, don't do that, you need to use a tunnel.
All right.
I've killed your job.
And what's the difference between, and this is from Vedant Query, you'd like to know what's the difference between a regular grid and a structured grid?
Well, regular, so if you're talking a Cartesian grid, for example, means that you have like unit spacing. But then if you have a different spacing, so you could have a grid that has like different spacing or something else, but it still has regular spacing as opposed to unit spacing like a Cartesian grid.
Okay. And also, could you explain what topological regularity is? Reference to slide 49.
Okay, yeah, I think that's kind of the same. Is it the same person? Yeah, that kind of just means that it's something that's repeating.
Okay.
Yeah, and so for example, if you look back on that slide, there's the example of a curvilinear grid. It's not, the cells are not identical, but it's described in some way, that is topologically regular. So the reason for that in Paraview, we bring all this up in terms of performance. If you can describe your grid in some compact way, other than just having a list of points and scalar values, that is better. You're going to save, it's more efficient to do that. So if you have any way to describe your grid, your underlying grid, other than just listing everything explicitly, that's better.
Okay.
So if there's any kind of, by topologically regular, I just mean, if there's any way that you can describe it as, like origin plus offset of some kind or something like that, you're going to be in better shape than if you have to list everything explicitly.
Another question is post-processing. Are you doing that on your local machine, or are we doing that on a remote machine?
Which post-processing?
In what you were running just soon.
Oh, that one, that example was just with the weather data, you mean?
Yeah.
That one was just locally on my laptop because that was a very, very small data set. But usually if it were larger, everything would just be done on the remote machine.
Okay. And another person, his name is actually Susholan Sen, which is awesome because that's what my first name is, Susholan. He'd like to know, are there any examples or case studies on using VR to visualize scientific data, like geospatial data, for example?
Case studies.
Or examples.
Yeah, I don't have any in this presentation. We had some projects actually this summer that dealt specifically with looking at water quality sensor data in VR. So we were working with some scientists that wanted to kind of keep the GIS framework from their data in VR. So if they want to contact me directly, I can talk to them more about that. I didn't include them in the slides, and we kind of just got started with that particular project. And I mean, there are definitely more projects like that exist that we didn't do personally, but the scientists that we worked with thought it would be extremely useful with geographical data to be able to have VR interface where you had the actual data linked in with the map data. So in the one with water quality, we had one that was water quality around the UT Austin area. And she wanted to be able to talk to the general public and legislatures to show data points for where they collected water quality, biodiversity data, and then the actual map data in one interface. So there was a project over the summer where we helped her, and then also had a similar project working with a watershed in Hawaii where pretty much the same thing. They wanted to kind of overlay different types of data to kind of give a connection between the actual data and then other data sets. So whether it be biodiversity or human impacts, or just to give people a sense of place. And then also the ease of being able to, we didn't get this far with the scientists we were working with this summer, but she wanted to be able to have all the different attributes she could look at. So from water sensor data, pH, and pH, ammonia levels, conductivity, and then just be able to kind of like swipe them into the view. So if you have a view that you're interested in, and be able to easily in VR change the view and change the data set, that was something that she wanted to do. So I feel like there's a lot of interest in that area.
Right. Kenneth Daniel would like to know, we gave a talk yesterday about various output packages for HPC. And which parallel output package would they, or do you see used most often for parity?
Probably HDF5.
HDF5?
Yeah.
All right. And then one last question. Is there a remote client support for anything like Visit or Paraview, where they can run Visit or Paraview locally on their machine, but have their data on a server?
Yeah, we don't support that here. There's the ability to do that, and often when you open up Visit, it asks you, do you want to set up a remote server? And we don't support that. I don't know if some other sites might do that, because it is possible, but we don't support that because it doesn't perform as well. So we recommend VNC.
All right. And one last one from Manu V. Great presentation, thank you very much. Any experience using NVIDIA grid technology, and how does that compare with VNC or NICE DCD? I'm not familiar with.
I haven't heard of NVIDIA grid technology.
Yeah, for that either.
Yeah, I don't know about that. So I don't know how it compares.
It's something worth looking into, because we're going to get those NVIDIA GPUs here soon.
Yes, so. Yeah.
All right. I think that finishes off us over here, Scott, if you want to take control back.
Well, thank you very much, Charlie and Ann, for a great presentation. You got some nice compliments on Slack, so thank you very much.